Welcome back to 5th lecture on Class 10 Science, Chapter 10, Light. In this video, we shall discuss diffraction by spherical lenses. So, a transparent material bound by two surfaces of which one or both surfaces are spherical is known as a spherical lens. So, basically, in spherical lens, there are two surfaces and at least one of the surfaces needs to be spherical in shape. Now, there are two types of lenses, convex lens and concave lens. Let's study about both of them in detail. First, let's discuss convex lens. So, it has two spherical surfaces, both bulging outwards. It is thick from the middle and thinner from the edges. It is a converging type of lens. This means that the rays of light meet at a point after refraction from convex lens. So all the rays meet at one point, that is known as the focus of the convex lens. And if you have ever observed a magnifying glass, so magnifying glass is a convex lens. If you touch the surface of magnifying glass, then you will feel that it is thicker from the middle and thinner from the edges.
Now let's discuss concave lens. So it again has two spherical surfaces, both curved inwards. It is thicker at the edges and thinner at the middle. And it is a diverging type of lens. This means the light rays tend to go away from each other after refraction. So in this way, we can differentiate between concave and convex lens.
Now let's discuss the terms related to lens. First, center of curvature. So the lenses have two spherical surfaces and each of these surfaces forms a part of a sphere. So basically, as you can see that lenses have two spherical surfaces, and if we complete the spherical surfaces, then both of them form a part of a sphere. And always a sphere will have a center. So there are two centers of curvature of lenses. And these are C1 and C2. You can see both the centers of curvature in both convex lens as well as in concave lens. Second, principal axis, denoted by P. This is an imaginary straight line passing through the two centers of curvature. Third, optical center O. This is a central point of the lens. You can see that the center of curvature is basically the center of the whole sphere, while the optical center is a central point of that lens. Fourth, aperture, denoted by A. This is the diameter of the circular outline of lens, as you can see in the diagram. Fifth, radii of curvature. They are the distances between C and O. So they are the distances between the centers of curvatures and the optical center. So as there are two centers of curvature, so obviously there will be two radii of curvature. Sixth, focus. So it is different for both the convex lens and concave lens. For convex lens, the definition of focus is that when several light rays parallel to the principal axis fall on the convex lens, they converge at a point on the principal axis. This is known as focus. So basically the point on which all the light rays converge after refraction from the mirror, refraction from the lens is known as focus. And again, the convex lens has two foci, f1 and f2, as you can see in this diagram. Now let's discuss the definition of focus for concave lens. So the point on principal axis where the light rays appear to diverge is known as the focus for concave lens. Again, concave lens have two foci, f1 and f2. Now the reason for having two foci is that we can either put the light rays from this side or either from this side.
And the last and seventh part of the spherical lens is focal length, denoted by small f. It is the distance of principal focus from optical center O.
So basically, if you recall that in the mirrors also there was a relation between the focal length and the radius of curvature. So again, in lenses we have a relation between the focal length and radius. That is, radius of curvature is equal to twice the focal length. Now let's discuss image formation by spherical lenses. So as we studied in the reflection by mirrors, again for refraction by spherical lenses, we first have to study the rules for making the ray diagrams, and then we will study image formation. So there are 3 rules, and let's study them. So let's study the rules for drawing the ray diagrams for a convex lens first. So as you know that here I have taken a convex lens. It is a bulging outward lens, so you can see that both the spherical surfaces are bulging outwards. And also here are all the parts of the lens. This green line is the principal axis. This center, this is the optical center of the lens, the central point. And here we are having the center of curvature C1 and C2, and here we are having the focus that are F1 and F2. So now, if you remember that there was a formula regarding the focal length and the radii of curvature. That says that the focal length is half of the radius of curvature, or the radius of curvature is twice the focal length. So now we can say that this center point will be nothing but 2f1. This is because the distance from here to here and distance from here to here is same. So we can write this as this central point as 2f1. Similarly, the C2 can be rewritten as 2f2. So now let's discuss the rules. The first rule says that if the incident ray is parallel to the principal axis, then refracted ray passes through the focus. So basically this is the principal axis, and let's draw an incident ray falling on this mirror parallel to the principal axis. Now when it will get refracted, it will pass through the focus. So as you know that convex lens is a converging lens, so this ray will converge and the ray will meet at the focus, that is F2 point. So this was the first rule, that incident ray is parallel to principal axis, then on getting refracted it will pass through the focus, that is F2 point. And if we extend it, we can extend it like this also. Now let's discuss the rule 2. So the second rule says that if the incident ray passes through the optical center, then the refracted ray continues along the same path and passes through the optical center without showing any deviation. So basically, if the incident ray is coming like this and passing through the optical center, then it will continue on the same path without showing any deviation, and it will pass through the optical center only. So basically, in this case, you can see that if the incident ray is passing through the optical center, then no refraction is taking place, no bending is taking place, it is continuing on the same path. This is our rule 2. Now let's discuss the third and last rule. This rule says that if the incident ray passes through the focus, then refracted ray is parallel to the principal axis. So basically, let's draw incident ray passing through the focus F1. So here on getting refracted, it will be refracted parallel to the principal axis. So you can see that this refracted ray is parallel to the principal axis. So after studying about the 3 rules for image formation by concave lens, let's study how can we form images. So again, we will use any 2 rules to get the 2 rays, and the image will be formed at the point where both of these refracted rays will meet. So now let's understand image formation by convex lens. Here I am having a convex lens with its optical center, its 2 foci F1 and F2, and here the centers C1 and C2, which can also be written as 2F1 and 2F2. So this is the base diagram. And now one important thing to ensure is that the distance between the F1 and O should be same as the distance between 2F1 and F1. So this distance and this distance needs to be equal. This is because the distance, because focal length is equal to half of the radius of curvature. And now first let's take the first case in which the position of object is given beyond 2F1. So basically here is our 2F1 point and the position of object is beyond this point. So let's take the point to be at this position. Here we have the object AB. And let's see the position of image and the nature of image so formed by using the first two rules of making the ray diagrams for convex lens. So let's use the first rule to draw the first ray. The first rule for drawing the ray diagrams says that if the incident ray is parallel to the principal axis, then the refracted ray will pass through the focus. And the second rule says that if the incident ray passes through the optical center, then it continues on the same path and passes through the optical center. So this is the point of intersection of both of these rays. So if you can carefully observe that this point is between F2 and 2F2 points. So from this we can tell that the position of image is between F2 and 2F2. And now let's see the nature of image. So the image formed will be inverted. It will be like this. This B dash A dash is our image. Now this is because the image is formed below the principal axis. So due to this, the image will be inverted. Also, as the rays are actually meeting at a point, that's why the image will be real. But however, this image will be slightly diminished. That is, it will be slightly smaller in size than the object. So this was our first case. Now let's discuss the second case in which the object is placed at the point 2F1. So basically, the object is placed at this point. Here we have object A. And now let's draw the two rays. First, using this first rule, we get that incident ray is parallel to the principal axis, refracted ray passes through the focus. Second rule, incident ray passes through the optical center, refracted ray continues on the same path. Now by using both of these rules, we get that they are intersecting at this point. So basically, if you draw a line, and we can see that this is B dash, A dash, this is our image. We can see that the image is formed at the point 2F2. So we will say that image is formed at the point 2F2. Now let's find the nature of image. Now here you can see that the image is inverted as it is below the principal axis, and also as the rays are actually meeting, the image is real. So real and inverted. And now let's find the size of image. So almost in this case, the size of image formed will be same size. So exactly if you try this experiment and draw these ray diagrams on your book, then you will, if you take the size of the object to be one line of your copy, then the size of image formed in this case will also be one line of your copy. That will prove that the image is of the same size as the object. Now let's discuss the third case in which the position of object is between f1 and 2f1. So let's take the position of object between 2f1 and f1. Here is our object A. Now using the first rule, we get that incident ray is parallel to principal axis and refracted ray passes through the focus. Using the second rule, optical center rule, we will get this second rule. So now here you can see that both of these rays are intersecting at this point. So they are intersecting here. Now if we draw an object, then this will be our object B dash. Sorry, if we draw the image, then this will be our image B dash A dash. Here you can observe that this image is quite bigger in size than the object. So it will be enlarged. And where is this image located? It is located beyond the point 2f2. Position of image will be beyond 2f2. Also, again, the image will be real and the image will be inverted. So, with this, we come to the end of the third case also. Now let's discuss the fourth case in which the object is placed at the focus f1. Here object AB is placed at the focus f1. The first ray will be like this. And the second ray will pass through the optical center. Zero point. And now here you can observe that both of these rays are not meeting here, but you can see that both of these rays are not parallel also. They will meet at some point afterwards. So we can say that they will meet at infinity because they are not completely parallel, but they are also not meeting at on a paper, on a board. That's why we can say that they will meet after a very long time at the point infinity. So the position of image will be infinity. Also, this time as it is meeting at infinity, the image will be very large in size. It will be very large, enlarged, highly enlarged, we can say that. And also the nature will be same, that is real and inverted, as the rays will actually meet at the point in infinity. Now let's discuss the fifth case in which the object is placed between f1 and the optical center. So the object is placed somewhat here. Now if we draw the two rays, then the first ray, incident ray is parallel to the principal axis, refracted ray passes through focus, and second ray, optical center ray. Here you observe that both of these rays are going away from each other. So if we keep on extending them in this way, then they will not meet anywhere. But you can also observe that if we make these rays in the backward direction, then they will meet at somewhere. So if we extend the rays in the backward direction, then both of these rays will meet. And here the object will be formed A dash, B dash. Now again, let's see the properties. The position of image will be on the same side of the mirror, on the same side of the lens, same side. The size of the image you can see is enlarged, and the nature of image you can see that this time these rays which we have extended backwards, these are not actual rays. We have just extended them, so we can say that both of these images are not actually meeting, they are just appearing to meet. So as the rays are not actually meeting and they are just appearing to meet on the same side of the lens, That's why we can say that this is a virtual image. Also, as the image is formed on the upper side of the principal axis, it is formed above the principal axis. So image is erect. That means the image is upright. So this was the fifth case, which was very interesting case. Now let's discuss the last case in which the object is placed at infinity. So to show that the object is placed at infinity, what we will do is that we will rub a part of the principal axis, and here we will display the object. Now this is because the object is at infinity. So to show that the object is at infinity, we have done this. Now whenever we show the ray diagram for object at infinity, we always use only the first rule. So if we can draw multiple rays using the first rule, that is incident ray is parallel to the principal axis and the refracted ray will pass through the focus. So in this case, all the rays will pass through the focus. So all the incident rays will meet at the focus F2. So that's why we can say that whenever the object is at infinity, the image is formed at focus F2. Also, the object is very small in size, point sized. And also the object is real as the rays are actually emitting, and always you can see that real objects are real images are always inverted. That's why this is the property. These are the properties of the image formed when the object is at infinity. The image is formed at the focus. So now let's learn the rules for drawing ray diagrams for concave lens. They are very similar to convex lens but slightly different. So here we are having a concave lens. It is a curved inwards lens. Both of its spherical surfaces are curved inwards. Here is the optical center O point of the concave lens. Here are the two foci F1 and F2, and the twice of the two foci that are 2F1 and 2F2. You can also write these as C1, center 1 and center 2. But for the ease of understanding, for the ease of reducing our variables, we are using 2F1 and 2F2 words. So let's start with our rule 1. So let's see what the rule 1 says. It says that if incident ray is parallel to the principal axis, then refracted ray appears to be coming from the focus. So let's draw and understand. Here we are having an incident ray that is parallel to the principal axis. Now, as you know that a concave lens is a diverging lens, so this ray will diverge. And when it diverges, you will see that it appears to be coming from this focus point. So it appears that it is originating from this focus F1. It is not in reality passing to that point, but when we extend it backwards, then it appears to be coming from the focus point. Now the second rule for drawing the ray diagrams of concave lens is same as the rule for convex lens. So in convex lens also the rule was same, that if incident ray is passing to the optical center, then refracted ray continues on the same path and passes through the optical center only. So no refraction takes place again in this case, and the rule is, again I will repeat it, that if incident ray passes to the optical center, then refracted ray passes to the optical center without showing any deviation. Now let's understand third rule. It says that if incident ray appears to go towards focus, then refracted ray is parallel to the principal axis. So this is basically the opposite of rule 1. This rule says that if incident ray appears to be going towards focus, then on refraction it will be parallel to the principal axis. So if we extend this ray, then it appears that it is going towards focus. It is directed towards focus F2. But on refraction, it will be parallel to the principal axis. This is our rule 3. So now let's understand the image formation by concave lens. So here we are taking two cases. The first case, the position of object is at infinity. So here we are having a concave lens with optical center f1, f2, 2f1 and 2f2. Now to depict that the object is at infinity, we will rub a part of the lens, a part of the principal axis, and here we will make our object. So here is our object AB at the point infinity. Now, as I told you earlier also, that for infinity case we always use only the first rule and we can draw n number of rays and all of them will meet at the focus. So we are using the first rule in which says that if the incident rays are parallel to the principal axis, then on refraction, this will be a case. And this line is passing the optical center only. This is like this. So this case, it will continue on the same path. Now here you can see that if we extend them backwards, then all of them are meeting at the focus F1. So the point F1 is the meeting point for all of the diffracted rays if we extend them backwards. So they are appearing to meet at the point at the focus F1. So position of image will be at the point F1 at the focus F1. But one important thing to note again is that this time the rays are only appearing to meet, they are not actually meeting. That's why the nature of image, it will be virtual, as rays are not actually meeting. Also, all virtual images are erect. And size of image will be again very point sized. So these are the properties of the image. Now let's discuss the second case in which the object is placed between point infinity and between O, between the optical center and infinity. So we can place it anywhere between infinity and O. So I am placing it at this point. Now here is our object and here we are using the first rule. We have got this ray, incident ray parallel to the principal axis. Refracted ray will appear to pass from the focus. And here using the second rule, we have got that incident ray is passing through the optical center and refracted ray will continue on the same path. Now here you can see that both of these rays are meeting at this point. So both of these rays are appearing to meet at this point. This point is basically A dash B dash. This point is basically between the point F1 and O. So when the object is between infinity and O, the image is between F1 and O. And you can see the size of image is smaller than the object, so diminished. Also you can see that this time again the rays are not actually meeting, they are just appearing to meet. So virtual image. Also you can see that the image is above the principal axis, that's why erect. So with this we have studied the image formation by both convex and concave lens. So this was all for today. I hope that you were able to understand the image formation and ray diagram.